So Stefan is the head of software at Sony Advanced Visual Sensing, where he's apparently mainly focusing on novel visual sensing solutions. So some interesting things to come out of that. We've heard, I think, a bit already about the collaborations between the University of Tokyo and Sony, some other processors. So I'm sure there's a lot more stuff hidden at Sony that they're working on.
It's a huge company, so there is a lot going on. Even us involved within Sony sometimes don't know all of the stuff that is actually happening within the company.
Nice.
Let's see. Can you see my slides?
Yep, your slides are good.
Wonderful, wonderful. So I'll be talking about how we at Sony Advanced Visual Sensing approach the design of our visual sensing systems. But let me start with an introduction of who we actually are first. Of course, Sony does not really need any introduction. You all likely know PlayStation, Sony Pictures, Sony Music, or our excellent cameras, TVs, speakers, or headphones. But what is much less known is that Sony is also world leading in image sensors. In fact, Sony Semiconductor Solutions is the world #1 in image sensor sales. And the portfolio of technologies of Sony Semiconductor Solution includes cutting-edge CMOS image sensors, depth sensors, event-based sensors, but also other related sensing technology. There are research centers spread across the world, and Sony Advanced Visual Sensing is one of these. So we are located near Zurich in Switzerland, and our focus is at the moment mostly on visual sensing systems that involve event-based cameras. And the reason for that is that our team has years of experience with event-based cameras. The majority of our team has previously worked at Insignis. If you remember us, this was a startup working both on event-based sensors, so on the hardware, and on event-based software targeted at applications such as collision avoidance, augmented reality, or virtual reality. If you're not familiar with event-based sensors, let me just give you a very quick explanation. For a more detailed and more broad explanation, I'll highly recommend the tutorial given by Davide Scaramuzza later today, if I'm not mistaken. But for now, the main property of event-based sensors is that each pixel reacts independently and only to changes in illumination. So what every pixel does, it tracks the amount of change in the infalling light since the last time that it has reacted, and it compares this change to fixed thresholds. Wherever the threshold is exceeded, a new reaction is triggered. And this reaction means that information is being sent out to the user, information that we typically call events, hence the name event-based sensors. So what we get as a user is a quasi-continuous stream of information where single pixels tell us that they have gotten brighter or darker and at which time. In this illustration, this animation here, we see a comparison of how a traditional CMOS imager perceives the scene and how an event-based sensor perceives the scene. The scene being this circle with a moving black dot, and many of you will have already seen that. It's a very famous example. And we can see that the traditional imager takes very familiar pictures at fixed frequency with certain exposure time. It will involve issues such as motion blur. If you want to increase the temporal resolution, it will involve a lot of data and a lot of power. And opposed to that, we have an event-based sensor which has a much higher temporal resolution, but it can only see the parts in the scene that are actually changing. So as this black dot is rotating, the pixels in the event-based sensor tell us they've gotten black, they've gotten white, and this is visualized as 2 dots here in the graph for data points where it has gotten brighter, and the red dots where it has gotten darker. And high temporal resolution is one of the main advantages of event-based sensors, and directly related to this, the fact that there is almost no motion blur. Additionally, thanks to how the pixels are actually designed, what we get from event-based sensors is a very high dynamic range and very low power compared to traditional image sensors. Now, what you might wonder is, if we have this sensor that only measures changes in the signal, what actually are the characteristics that we can get out of this sensor? What are the applications that we can use it for? To discuss this, let's have a look at this somewhat illustrative equation. What you want to visualize here are the different parts that make up the changes that are then being sent out by the sensor as events. On the one hand, just the presence of an event, the fact that the illumination has changed by a certain amount, is already very interesting information. It can be used as entropy cues and can be used downstream for things such as smart processing, smart triggering, and wake-up calls, as I will be discussing a bit later in the talk. If you look at the signal, on the other hand, we have, roughly speaking, 3 potential causes of the change of the illumination that falls on the pixel. One, straightforward, is that the light in the scene is changing. Another could be that the reflectance is changing. And then yet another, that there is motion in the scene. And due to the fact that the scene is textured, this actually causes a change in illumination falling on the different pixels. Now, with all of these parts in the signal, we can do different things. If we can control the light that illuminates the scene, we can do things such as active lighting, we can do structured light, we can do active marker tracking, we can do visual light communication. I'm not so sure what we could do by looking at reflectance changes, maybe tracking changes on the skin of a chameleon, but that's maybe not that relevant. More relevant likely is looking at the remaining part, which encodes spatial contrast together with optic flow, with the information of motion per pixel. Now, using appropriate algorithms, we can indeed decouple these 2 components and estimate them just based on the events. So we can do things such as tracking, estimating the pose of the camera or of objects in the world, and we can reconstruct the scene as well. Now, what we're really interested in at Sony AVS actually is how can we combine our event-based sensors with the other sensors that are being designed within Sony, be that conventional cameras, be that depth sensors. How can we build the best system for any given application that can exploit the different advantages while balancing the challenges that all of these sensors actually bring, such as a lower temporal resolution for the camera or the depth sensor, or the fact that if the sensor and scene is not moving at all, event-based sensors don't see anything at all. Once we have figured out how to optimally combine these different modalities, the next step to building an actual system, an actual product, is to figure out how to map the different parts of our algorithm to the compute resources that are available. And here is an abstract diagram of typical compute resources found in, for instance, mobile products. So let's have a look at what capabilities and constraints these processing entities actually provide and what we can learn from that. This is only going to be a bit of a high-level discussion, but still I think it's very relevant to understanding how to design an overall system that is efficient and can sufficiently address the challenges present, especially in the real world. Nowadays, sensors can support more and more logic at a very low level, very close to the pixels, also in commercial products. but still typically they're accompanied and supported by dedicated, sophisticated and specialized co-processing units that can do one thing only, but do this very, very well, such as image signal processing or running a neural network. And of course, typically there's more than just one coprocessor, and it does also not necessarily need to be separated as in this figure from the sensor. They could also be integrated together. Overall, the target typically is, if we have our algorithms, we would like to have as many blocks as possible to be running on these two components. Whatever is left needs to be pushed downstream to the general purpose application processor, which is typically a shared resource. And we don't want to take resources away from user applications such as the apps running on a smartphone or another mobile device, be that a robot, drone, whatever it is. So overall, putting it very simply, what we can say that the closer to the sensor, the more simple, specific, and specialized operations would be. But at the same time, they're also typically more efficient and use less power. So clearly, if we have our algorithm that nicely fuses different modalities, what you'll want to do is to push as much of the processing upstream to sensor or coprocessors, and also rethink different building blocks, how they're computing and whether they could actually potentially be computed on another cheaper, more specialized block. What we, however, further do to optimize our system is to rethink when each of these blocks does actually need to be computed. So the question that we pose is when to actually compute. And the typical paradigm in visual sensing is that this is all rate-based. We typically have rate-based sensors. We have cameras, we have ToF sensors running at fixed rate. We have IMUs running at fixed rate. They produce their data. It's being passed on to software building blocks. They process it, pass it further down. All of that happens at a fixed rate. And the whole system does not really care whether it's really necessary to run all of these computations. If we are tracking something, if we are doing pose estimation, why would we retrack and rerun the whole pipeline if the whole system is standing still? So clearly a more modern approach tries to minimize the amount of unnecessary processing using adaptive updates. And this can happen from both sides. So on the one hand, we can use the application processor and have it asking the sensing system for new updates. Why should there be a new update if the application processor, if the downstream application has no use for it? So we can achieve or target a somewhat optimal sampling at the output. And then opposite to that, the obvious other side is the sensor. If we have smart sensors at the input, they can actually make the whole system aware of relevant and interesting changes and basically create interrupts and trigger updates downstream. And thinking this further, it's not just the application running at the end or the sensing modality that is at the beginning of the whole pipeline. Every block within the pipeline can do the same thing. Every block that has data's input and data's output can decide if it receives new input data, whether it's the right time to now actually run its computations. And if it does run the computations, whether it's the right time to pass this data onwards downstream. And it can also figure out whether it is necessary to potentially ask the blocks upstream for new data. One example of that would, for instance, be if we have an estimate with an according uncertainty and the uncertainty is growing, we might ask the sensor to provide new data. So having mapped out these different considerations allows us to map our algorithms to hardware and pick appropriate designs. And you might have already figured that clearly fully reactive updates are a very nice fit, especially for event-based sensors. But let's have a look at two specific examples. One very prominent use case in computer vision is tracking. If we go back to our illustrative equation from earlier in the presentation, let's for now forget about changes in illumination or reflectance and just focus on this last term. What we need to figure out for tracking is, on the one hand, the gradients that are present in our scene, and on the other hand, the motions per pixel. And if you look at our modalities, we quickly realize that spatial contrast is very easy to figure out if we have an image. So it makes a lot of sense to use a CMOS imager to calculate spatial contrast. And at the same time, optical flow is something that causes motion, that causes change. So this is likely an interesting use case for event-based sensors. And indeed, if we throw a general purpose tracking algorithm, even just at a very simple task, such as what we have seen from the visualization at the beginning, but in reality, so a moving dot spinning, we can use that to visualize a bit better advantages of how these two modalities can complement each other. So in the left-hand side, you see it running roughly in real time. On the right-hand side, a bit another moment in the data in the video, but it's slowed down. And what we can see here is in the visualization, again, the events are displayed as red and blue data points for brightness changes in a more brighter and darker direction accordingly. And we can see the sparsity of this data and also the high temporal resolution that allows us to track these points. And at the same time, we also see that while the frames do not exhibit any severe motion blur, there's actually too much motion in between frames to properly allow to track these points just based on frames. So this is a clear example of where adding events actually enables the tracking, the proper and successful tracking in the first place. Of course, this also generalizes to other challenging scenes that are maybe more relevant in real scenarios. We see here two videos where event-based tracking based on both events and frames is successful, while a standard Lucas Canade approach here, the implementation from the OpenCV library, actually fails in shaky and very fast motions, but also if you try to track high frequency textures. And what is important to mention here is that the event-based tracking works without any need to co-estimate a camera pose, without the need for a motion model or motion priors, without any need to ensure certain spatial coherence in between features. It's really just the high temporal resolution of events that enables this. But thinking back about our design considerations, what might such a system actually look like if we map it to the processing that we have available? And again, remember what we try to do is to do as much of the processing as possible on sensor and co-processing. And at the same time, we want to run the different blocks that compromise the algorithm as few times as possible in order to minimize the power consumption and potentially improve latencies. Now, for feature tracking, it seems quite obvious that there's no and really absolutely no reason why we would update a feature track if nothing is changing. And the nice thing is that events directly tell us when something is changing. So it stands to reason that it makes a lot of sense to use the events to trigger updates at the times at which our feature positions are actually being computed. The grayscale or frame information, on the other hand, is only needed for gradients. So we don't need it at any other moment, but when we have need for new gradients that we are not yet that we have not yet computed. So in terms of processing, very low level, close to the sensor, what we might try to do is to do some basic noise filtering to ensure that only the necessary events are being propagated on. And then typically we have a stage where events are accumulated. And following this stage, we need to decide when we actually want to run the update. And now, given the fact that we do know the gradients for this feature, we can obviously figure out which events and how many events we indeed need in order to have all of the degrees of freedom of the transformation that we're using in the feature tracking constraint. And before having all of these events, it does not make any sense to run the update. Furthermore, we can push this even further down, such as to a decision that we would like to do the update every 1 pixel flow or every 2 pixel flows, just to kind of constrain the amount of compute that we will have to spend. And this nicely scales the compute, as we will spend more compute if there's more motion, but no compute if there is no motion. So this is a very nice property. Now I'm going to run just a little bit over my 20 minutes. I hope this is okay. I would like to discuss just one more example. In this example, we have discussed sensor fusion of event-based sensors with a camera. What if we wanted to do fusion of a camera with a depth sensor, in this case, a time of flight? A time of flight has, similar to cameras, a comparably low temporal resolution, but it uses even more power because of the need to illuminate the scene. So clearly, the high temporal resolution and low power of event-based sensors look as if they are a very nice addition to such a system. So we could try to do two things. If we can use the events to predict depth, what we can do is to either boost the spatial resolution of our depth output, or we could save power by replacing depth measurements of the ITOF sensors with predictions of our events. And this actually can work. You can use a neural network. You can feed it with a depth frame, a starting point, and then with following events, and predict what the depth would actually look like. And this is what you can see in this video here. So on the left-hand side, we can see the events measured by the sensors. There's the ITOF frames in the middle, but only at the beginning, the ITOF frame is actually being fed into the neural network, and then the neural network uses the events to predict what the depth would actually look like. You can see that in this case, the temporal resolution here on the right-hand side is much higher compared to the temporal resolution of the ITOF sensor. And again, if we look at how we can match the different blocks that would be involved in such a systems to our processing, we get a similar picture. We can again use this reactive and adaptive sensing and update paradigm to optimize the compute that we actually need. And here it really depends on our requirements. If we have an application that needs a fixed rate depth output, then clearly the dominant triggering source would be the demand from the application. But on the other hand, if you were trying to save compute, then again, it makes sense to look at the number of events that are actually happening in the scene. And this is because if there are no events, there's likely no changes in the scene, so likely also no changes in depth. So why would we recompute any depth? And if there are only very few events, then likely the predictions based on these events would not be really good, and it makes more sense to just every once in a while capture a new time of flight frame. On the other hand, if you get a lot of events, this would mean that there's a lot of changes in the scene, and very likely the temporal resolution of the ITOF cannot sufficiently sample this motion anymore. And in such a case, it would make a lot of sense to use regular updates based on the events to boost the output of the depth, and hence overall, again, optimize the sensing system using this adaptive and reactive paradigm based on what we can do using event-based vision sensors. Now, with that, I'm at the end of my presentation. If you are interested, please follow us on LinkedIn, and we would also be delighted to see you in an interview and join us at Sony or even Sony Advanced Visual Sensing. So thank you very much, and I'll be ready for questions.
Excellent, thank you. Thank you for a great talk. As ever, please put your questions in the chat, and I'll kick us off with, so you're talking about using applications to sort of pull information from the coprocessor and lower systems, but would that add in latency to the whole pipeline? And would that present a problem in a lot of applications where actually you'd rather have the most up-to-date information, even if you sometimes throw it away?
Yes and no. I guess you could also try to have downstream in the end application an algorithm that is actually able to predict upfront that information will be needed. So in many cases, you would actually know the dynamics of your system, and through that, you could actually figure out at which point you would need new information. So not necessarily, but yes, if it's only reactive in the sense, oh, hey, shit, I have too much uncertainty in my system, then it's probably already too late to ask for new information.
Yeah, interesting one. Second question I had was, how do we make event cameras and things sort of robust to sort of natural phenomena in lenses like lens flare or overexposure? Sort of what happens when we reach the limit? So, you come out of a tunnel and everything goes, all the events happen at once because everything's bright for a second? Or is that something that is coped sort of implicitly by event cameras?
I believe the tunnel example is maybe not the best one, since basically there you would just have this bright dot that starts extending, and this is just like a high dynamic range scene that can be handled very well by event-based sensors, as can be seen in various videos in the literature in academia, but also in the industry. On the other hand, things such as lens flare are the same problem as on standard CMOS image sensors. So this is not really my field of expertise, but we have some of the best engineers in these areas within Sony. So I'm lucky to say that we can rely on that expertise to properly coat lenses, to properly design the overall system, to at least limit the effect of these phenomena.
Cool. So where do you think the public is going to first see this sort of technology being used? I mean, is it the sort of thing that is going to be on Sony cameras, or do you reckon it's going to be more in the sort of commercial robotics space?
I believe across the board, just if you look at the development of computer vision in the industry, a lot of is focusing on compute, on saving power with all of these mobile devices. And if you run a SLAM or pose estimation, they're just going to be out of power in no time at all. So whatever can be used to push down this power and at the same time even improve robustness, for instance, in the presence of fast motions, is very, very promising. So I really believe that we will be seeing event-based vision sensors entering products, and well, let's see.
Excellent. Oh, we have a question. What can you say about the short-term roadmap for event sensors? Are they going to be higher resolution? Are we going to go for small form factor or higher energy efficiency? Where are the priorities for the short-term goals?
I can not say too much, but if you look at what's been coming out, I think there are some tendencies that are typical also for other image sensors. We start to see higher and higher resolutions, and at the same time, pixel pitches are going down to a certain degree, enabling these higher resolutions in the first place. So these developments definitely happen, yes.
Is there room, do you think, for event cameras that they are often sort of pixel-based events? Do you reckon it's possible as the resolution gets higher, you're going to end up with lots of pixels near each other all firing, or having events? Is there room for more of a hierarchical approach where you have sort of larger events that can compress the information of a few pixels all into one update that can then even further reduce the data transmission out of the camera?
This is a very interesting question, especially it basically relates to how would you downsample event-based data. And it's maybe not as straightforward as for image sensors, since especially if you don't actually know what the absolute values in illumination are at every moment in time, the actual absolute change in illumination represented by events that are neighboring each other can differ quite a lot. So if you were to basically put them together in a at a higher level in a event-based image pyramid, it's not quite clear how to fuse that. I think this is a topic of research in both industry, but probably also academia, how to properly do that. And it's certainly interesting, though. You might have noticed, if you have worked with event-based sensors, that yes, they are power efficient. Yes, they do not produce a lot of data relative to the temporal resolution, but due to the high temporal resolution, if there's a lot of change, they actually produce high and really high spikes of data, which place quite a high burden on the processing downstream. So these sort of problems need to be tackled.
Awesome. Well, thank you again for your excellent talk. I think
thank you very much for having me.
Yeah, thank you for coming.